Mandibular movement recording is a crucial technique for reducing occlusal adjustments in splint design by precisely documenting how.
Hello everyone, thank you for joining us today. My name is Jenny and I'm a part of the education team at Medit. Nice to meet you everyone, and today we have Dr. Kim here.
Hi Jenny and welcome everyone. It's a pleasure to be here.
So many of you might remember the Hughes webinar series about how to reduce chair time. So it was consist with 5 parts and it was a big hit. So thank you for sharing all your tips and common errors that can easily occur in daily practice.
Yeah, as most of daily practices has been replaced by digital methods, every work process has become much simpler, but needs caution at certain points. So I try to inform Medit users about all the mistakes I had gone through so that the same issues won't happen to you. So I feel great that you all loved this series.
Yeah, of course. We also loved all the contents about small experiments that you did in your clinic. It was really interesting and definitely that helped us to understand the whole situation much better.
I feel so grateful. Thank you.
Yeah, okay, so let's talk about today's topic. So Dr. Kim came back with a topic about splints. So do you often do splint treatment in your daily practice?
Yes, I think restoring splint become much easier with the help of digital devices. So I'm going to talk about Medit Splint app and vector to reduce check time when processing splint.
That's really interesting that producing splints became much easier when it becomes to digital dentistry. So I would like to hear about it soon. Shall I begin, doctor?
Sure.
In this lecture, we aim to introduce the overall workflow of creating splints digitally with a particular focus on checkpoints to reduce clinical time. This lecture is structured around 2 main themes: workflow and considerations, aimed at providing a comprehensive understanding of both the procedural flow and the critical evaluative process in our field. We begin by exploring the workflow. This section aims to outline the entire process from initial concept to final outcome. We'll delve into the key steps involved and discuss how each phase seamlessly connects to ensure a smooth project lifecycle. The second part is dedicated to considerations that must be addressed to achieve the best possible outcomes. This includes focusing on improving wear comfort and the overall appeal of the product to satisfy both patients and practitioners. The objective throughout this lecture is not only to impart technical knowledge but also to foster an understanding of the strategic decision-making process that underpins successful outcomes in our practice. Preparing a lecture on the process of creating occlusal splints using an oral scanner and a 3D printer involves several key steps. This process can generally be broken down into the following phases. 1. Patient evaluation and preparation. Before creating an occlusal splint, evaluate the patient's oral health and identify the specific issues needing treatment. If necessary, proceed with teeth cleaning or other preparatory steps. 2. Oral scanning. Use an oral scanner to create a 3D image of the patient's teeth and oral structure. This non-invasive process is comfortable for the patient. The data from the scan is used to generate a digital model essential for creating an accurate occlusal splint. 3. Design and modeling. Based on the scan data, use CAD, computer-aided design, software to create a design for the occlusal splint tailored to the individual patient. This step involves determining the shape and size of the splint to provide optimal fit and functionality considering the patient's oral structure and needs. 4. 3D printing. Send the designed occlusal splint model to a 3D printer, which converts the model into a physical object. This process typically involves dental materials such as photopolymer resins, utilizing precise layering techniques to produce a detailed final product. 5. Post-processing and finishing. After 3D printing, the occlusal splint may undergo additional post-processing steps if necessary. This can include removing any support structures, smoothing, and sterilizing if required. 6. Fit testing and adjustment. Fit the created occlusal splint to the patient and make any necessary adjustments. This step is crucial for ensuring a perfect fit and optimal comfort for the patient. 7. Care and usage instructions. Provide the patient with guidance on the correct use of the occlusal splint, including how to clean and maintain it. When creating an occlusal splint, the intraoral scanning process is critical as it captures the precise dental anatomy of the patient. 1. Preparation. Before scanning, ensure that the patient's oral cavity is clean and dry. Remove any removable appliances and check for saliva or blood. Position the patient comfortably and explain the scanning process to alleviate any concerns. 2. Maxillary arch scanning. Start with the occlusal surfaces, moving from the first molar of one side to the other side. Scan the palatal surfaces next, and then the buccal surfaces. Ensure to capture the gingival margin for the occlusion stage. 3. Mandibular arch scanning. Similar to the maxillary scan, start with the occlusal surfaces. Proceed to the lingual surfaces and finish with the buccal surfaces. 4. Bite scan. After scanning both arches, it's necessary to record the patient's bite. Ask the patient to bite down in a centric occlusion to capture their natural closure. This scan helps in aligning the maxillary and mandibular scans accurately. Mandibular movement recording is a crucial technique for reducing occlusal adjustments in splint design by precisely documenting how the jaw moves in all directions without opening the mouth. This method allows for a more accurate assessment of the patient's occlusion, capturing the natural dynamics of jaw movement. The recording process involves the patient keeping their mouth closed and using a scanner to document jaw movements as they move their jaw forward, backward, left, and right. This approach captures the jaw's natural movements, providing a true reflection of the patient's occlusal state. The information obtained from mandibular movement recording enables accurate predictions of occlusal alignments, reducing the need for adjustments in splint production. This technology allows dental professionals to provide customized treatments, improving the patient's treatment experience. If you found this video helpful, please subscribe to our channel for more insights and updates. Using the Medit Splints app for designing splints involves selecting a case in Medit Link, opening it in the app, choosing between auto creation or manual creation for the splint, and following the guided steps for each option. Auto creation utilizes AI for efficiency, while manual creation allows for detailed customization. Further refinements and adjustments can be made to ensure the splint meets specific requirements. To run the Medit Splints app from Medit Link, you select a case within your Medit Link account, either from a clinic or lab account. The Medit Link platform integrates with the Medit Splints app, facilitating a streamlined workflow from case selection to splint design. This process leverages the seamless connection between Medit's software ecosystem, allowing for efficient management and creation of dental splints. Assigning data in the Medit Splints app involves selecting the specific case you want to work on from MeditLink and then utilizing that selected scan data for splint creation. This process is a crucial step before you begin designing the splint, either through auto creation or manual creation, as it ensures the app has the necessary patient-specific information to generate a precise and customized splint. When you're ready to create a splint using the Medit Splints app, you'll first need to choose which arch the splint will be for and the type of splint required. There are three main types: Michigan, flat plane, and anterior bite, each with its own specifications affecting the outline and surface of the splint. When designing an occlusal splint using the Medit Splints app, the process can be undertaken using either an auto creation workflow or a manual creation workflow. With auto creation, the application utilizes AI to streamline the process. The auto creation process follows a sequence of overview mode, design mode, and labeling mode, although design and labeling modes can be skipped if you are satisfied with the automatically generated splint. The parameters in this mode, such as the occlusal adjustment, inner surface offset, and smooth surface, come with default values that you can later adjust to fit your needs. On the other hand, the manual creation route offers more control over the splint design process, allowing you to make fine adjustments and alterations. This process involves several stages, including overview mode, edit mode, and alignment mode, which can include additional steps like occlusal adjustment mode and inner surface creation mode. The inner surface creation involves setting parameters for blockout direction and amount, inner surface offset, and smoothness, all contributing to the fit of the splint. In the alignment mode of the Medit Splints app, you'll align the scan data to the virtual occlusal plane. This step is crucial for ensuring the splint fits accurately within the patient's mouth. The app can automatically perform this alignment, but manual adjustments are possible for precise control. If the alignment is already done in the Medit Scan software, you can opt to skip this step, although it's advisable to double-check for accuracy. The tool allows for alignment by selecting 3 or 4 points on the occlusal plane, which can be particularly helpful when there are no anterior teeth present. The Medit Splints app also incorporates features like occlusal alignment mode, where you adjust the occlusal relationship to create space for the splint. The occlusal adjustment mode in the Medit Splints app is about modifying the occlusal relationship between the upper and lower teeth, maxilla, and mandible, creating the necessary space for the splint. This mode is essential when the occlusion is not in an open state or if both arches are present. The adjustment is done by setting the distance to the antagonist, the closest point between the upper and lower teeth when the mouth is closed, and the bite opening in the virtual articulator, ensuring there is sufficient space for the splint with appropriate occlusal thickness. The inner surface creation mode is where you define the fit of the splint by adjusting retention and offset. In the Medit Splints app, the inner surface creation mode is used to refine the inner surface of the splint. In this mode, you can adjust the blockout amount and direction, inner surface offset, and the smoothness of the inner surface to ensure a precise and comfortable fit for the splint. The retention slider allows you to set the extent of undercut areas for better retention of the splint. The preview function helps visualize the adjustments before finalizing them. This mode is essential for creating a splint that fits snugly against the patient's teeth. In the outline designation mode of the Medit Splints app, you delineate the perimeter of the splint along the buccal, cheek side, and lingual, tongue side, aspects of the teeth. This is accomplished using automated tools within the software, with sliders to adjust the outline proximity to the gingiva. If adjustments are needed, you can manipulate control points directly on the outline. The goal is to achieve a green outline, indicating a successful path for the splint's border. Red lines suggest areas needing correction. Once the outline is satisfactory, you proceed to the next step in the design process. The outer surface creation mode is where the thickness of the lingual and buccal surfaces is adjusted, and the smoothness of the outer surface is defined. In the outer surface creation mode of the Medit Splint app, you define the thickness and smoothness of the splint's outer surface. Adjustments are made using sliders for the lingual and buccal thickness and for the smoothness of the surface. Additionally, for printers with multi-jet technology, you have the option to create a dual-layer splint, separating the design into inner and outer layers for different material properties. In design mode of the Medit Splint app, you can finalize your splint design. This includes analyzing occlusal contact points and adjusting the splint to eliminate any intersections with opposing teeth. The mode offers tools for sculpting the splint's surface and measuring thickness to ensure accuracy and comfort. Once the design is satisfactory, you can proceed to the next step in the workflow. In the labeling mode of the Medit Splint software, you can add, edit, or delete labels on the splint. The mode offers tools for these functions, such as managing label placement and choosing font and size. You can emboss or engrave labels onto the splint, and up to 6 labels can be added. The position and depth of labels can be adjusted to ensure they are correctly placed before finalizing the design. Let's take a look at the process of outputting a design file. Export phase. The first step in the 3D printing process is to export your design. This involves preparing your digital model in a 3D modeling software and exporting it in a format compatible with your 3D printer, typically STL or UBJ. Slicing phase. File import. Once your design is exported, the next step is to import the file into slicing software. This software converts your 3D model into instructions that the printer can understand. Angle adjustment. To ensure the best print quality and strength, it's important to adjust the angle of your model. We'll show you how to rotate your model for optimal printing. Support addition. For models with overhangs or complex geometries, adding supports is crucial. We'll guide you through adding supports to ensure your model prints correctly. Profile selection. Next, select a printing profile. This determines the resolution, layer height, and print speed, among other settings. Choosing the right profile is key to achieving your desired finish. Slicing. After setting up your model, it's time to slice it. This process converts your model into layers and generates a G-code file, which is what the printer will use to print your model. Printing phase. With your model sliced, it's time to print. Load the slicing file into your printer and start the print. We'll show you how to select the file on your printer and discuss the importance of monitoring the initial layers for adhesion. Post-process phase. Plate removal. After printing, carefully remove your model from the build plate. We'll demonstrate techniques to do this safely without damaging your print. Cleaning. Next, clean your model to remove any residual material. Depending on the type of printer, this might involve washing with solvents or water. Support removal. Once clean, remove the support structures. We'll show you how to do this without leaving marks or damaging your model. Post-curing. Finally, For some materials, post-curing under UV light or heat is necessary to achieve the final strength and surface finish. We'll cover the basics of post-curing and how it enhances your model's properties. In this presentation, we will explore the essential factors to consider when fabricating dental splints: retention, appropriate thickness, printing angle, and methods for achieving a transparent and glossy surface. Retention is crucial for ensuring that the dental splint remains securely fixed to the teeth, providing comfort for the patient and maximizing therapeutic effectiveness. Enhancing retention can be achieved through optimizing the splint design. In this section, we delve into the intricacies of the insertion path and margin line, two pivotal factors in dental splint design that significantly influence retention, patient comfort, and overall treatment efficacy. The insertion path is a key concept in the design and application of dental splints, focusing on the angle and direction for placing or removing the splint. This aspect is vital for minimizing resistance during insertion or removal and ensuring the splint fits perfectly. A primary consideration is the relationship with undercuts, as this directly impacts retention. The aim is to achieve an even distribution of undercuts across all teeth, ensuring the splint engages effectively with these areas. For the upper arch, it's important to ensure that undercuts start from the middle of the buccal surfaces. This positioning helps in achieving balanced retention. Aligning the splint parallel to the long axis of the teeth is another critical aspect. This alignment, coupled with avoiding soft tissue impingement, ensures patient comfort and splint stability. Finally, customization of the insertion path based on the individual's anatomy and the specific design of the splint is essential. This ensures ease of use and stability, catering to the unique needs of each patient. Undercuts in dental anatomy are critical for the retention of dental splints. They offer natural contours that allow the splint to fit securely around the teeth. The goal in splint design is to achieve a uniform distribution of undercuts. This uniformity ensures the splint engages with the teeth effectively, providing optimal retention without causing patient discomfort. When setting the insertion path for a dental splint, it's essential to navigate these undercuts delicately. This careful navigation ensures the splint can be inserted and removed easily by the patient or dental professional, while still maintaining a secure fit on the teeth. The balance between a secure fit and ease of insertion and removal is paramount. Ensuring this balance is key to the successful application and functionality of dental splints in patient care. The placement of the margin line is critical for both the comfort of the patient and the functionality of the splint. It requires precise positioning to achieve the desired outcomes. Including undercuts within approximately 2 mm of the margin line is essential for ensuring effective retention. This allows the splint to engage with the teeth properly, securing it in place. It's important to avoid impinging on the gingiva. This consideration helps in maintaining patient comfort and makes the splint easier to clean, thus contributing to overall oral hygiene. The margin line should closely follow the contours of the gingiva while remaining above the gum line, supragingival, to prevent irritation or inflammation, safeguarding the patient's oral health. The positioning of the margin line may need adjustments based on the specific purpose of the splint and the unique anatomy of the patient's mouth. This customization ensures a secure and comfortable fit tailored to individual needs. We're examining how adjusting undercuts and margin lines affects the retention of dental splints, particularly across different dental sections such as the anteriors, premolars, and molars. Our approach involved creating 4 distinct splint designs, each varying in the distribution of undercuts and the inclusion or exclusion of these undercuts by the margin line. This methodical approach allowed us to evaluate how these factors influence retention in vital dental areas. The findings were clear. Splints with uneven undercut distribution suffered from inconsistent retention, affecting both the stability of the splint and patient comfort. In contrast, the designs that featured an even distribution of undercuts, with the margin line incorporating these undercuts, showed superior retention. This design ensures uniform engagement with the teeth, providing stable fixation and enhancing patient comfort. The takeaway from our research is the critical importance of meticulous planning in the design of dental splints. Achieving even undercut distribution and ensuring that the margin line includes these undercuts are fundamental to optimizing the retention of dental splints, ultimately contributing to improved patient comfort and therapeutic outcomes. When designing dental splints or any dental appliance, the inner surface parameters play a critical role in determining the fit, comfort, and functionality of the final product. Here's a breakdown of the 4 options you mentioned. The inner surface offset is a crucial parameter in designing and fabricating dental splints. It represents the gap between the actual surface of the tooth and the inner surface of the splint. Proper adjustment of this parameter is vital to ensure that the splint fits precisely on the teeth. It plays a significant role in compensating for any errors that might occur during the printing process, which is crucial for a comfortable fit without causing tightness. A correct offset is essential for the splint's functionality and the patient's comfort. It considers the thickness of the material and any necessary adjustments for specific treatment requirements or to enhance patient comfort. If the splint is found to be too tight or not fully seated, the offset value should be increased. Conversely, if the fit is too loose, the offset value should be decreased. This adjustment capability allows for a custom-fit appliance that meets the patient's needs. Therefore, determining the right inner surface offset value is key to delivering optimal treatment outcomes. This involves balancing the need for a snug fit with ensuring patient comfort and the effectiveness of the splint. The smoothness of a dental splint's inner surface significantly impacts both its functionality and the comfort level experienced by the patient. Adjusting this parameter is a crucial step in the design process. Reducing the smoothness of the splint's surface enhances its ability to adhere to the teeth, which is especially beneficial for patients with evenly aligned teeth. This closer fit improves retention without sacrificing comfort. Conversely, for patients with irregularly aligned teeth, increasing the surface's smoothness may reduce the splint's grip. However, this can make the splint more comfortable and tolerable by minimizing irritation. It's important to strike an optimal balance between surface smoothness and the need for adequate retention. This balance ensures that the splint remains stable and effective in its therapeutic role while also being comfortable for the patient. Adjustments to the smooth surface parameter should be made with careful consideration of the individual's dental alignment and specific comfort needs, aiming to achieve the best possible treatment outcome. The angle parameter is crucial in dental splint design, as it sets the orientation of the splint's inner surface in relation to the teeth and gums. This orientation directly impacts how the splint fits and functions. Its primary influence is on the engagement between the splint and the tooth undercuts, as well as how the splint fits around the gingiva. Proper engagement is key to the effectiveness of the splint. Adjustments to the angle parameter can significantly enhance the splint's performance. By ensuring accurate engagement with the tooth's contours and undercuts, retention is increased, leading to a more secure fit. Furthermore, these adjustments improve the splint's stability and reduce the potential for pressure or discomfort on the patient's gums and teeth, contributing to a better overall user experience. Strategically increasing the angle reduces the offset. This closer engagement with the teeth enhances retention, crucial for the splint's effectiveness. Properly adjusting the angle is also vital for effectively blocking out undercut areas, ensuring the splint engages with the teeth where retention is strongest without causing discomfort. The retention slider is a tool for setting the degree to which undercut areas are utilized to secure the splint in place. This adjustment is crucial for optimizing the splint's retention capability. By defining the thickness of protrusions in the undercut blockout areas, the design directly influences the splint's ability to remain securely over the teeth. These protrusions are designed to engage with the natural undercuts of the teeth without causing discomfort. As the thickness inside the undercut areas increases, the overall offset decreases. This decrease in offset results in a tighter fit of the splint on the teeth, thereby enhancing retention. This adjustment is vital for ensuring the splint remains in place, providing consistent therapeutic benefits and comfort to the wearer. When using the auto creation feature in Medit Splints, the app will prompt you for feedback on the most recent splint design. The app will take note of your response and make automatic parameter adjustments to produce a more precise splint design the next time. It automatically adjusts parameters, like modifying the inner surface offset by 0.02 mm to enhance the precision of future splint designs. This iterative process aims to improve the overall design quality based on user experience and feedback. When a dental splint feels loose or is easily dislodged, several factors should be examined to improve its fit and function. First, check the distribution of undercuts by adjusting the splint's insertion angle. A balanced distribution front and back is essential for effective retention. Next, ensure that the margin line sufficiently extends beyond the undercuts, ideally by 2 mm. This extension is critical for securing the splint in place. If the splint is overly loose, consider reducing the inner surface offset and the smooth surface settings. These adjustments can increase the splint's adherence to the teeth. Conversely, if the splint is not particularly loose but tends to dislodge easily, enhancing the angle and retention settings can provide a more secure fit. When encountering a splint that does not fit or feels too tight, adjusting the inner surface offset and the smooth surface parameters can provide a solution. Increasing the inner surface offset creates more space between the splint and the teeth, alleviating tightness. Enhancing the smooth surface parameter reduces friction, contributing to a more comfortable fit. For a splint that is secure but not too tight and does not easily dislodge, reducing the angle and retention settings can help fine-tune the fit. Lowering the angle can reduce the direct engagement with undercuts, preventing the splint from being overly snug. Adjusting the retention parameter downward minimizes the intensity of engagement within the undercut areas, ensuring the splint remains secure without excessive tightness. The thickness of the dental splint should balance patient comfort with effective treatment. Too thin, and it may break easily; too thick, and it can cause discomfort. Typically, a thickness between 1.5 mm to 2 mm is considered ideal. When designing 3D printed occlusal splints, understanding the mechanical properties of the material is crucial. This ensures the splint has the necessary strength and functionality, The balance between the material's flexural strength and its surface hardness is critical. Flexural strength indicates the force the material can withstand without bending, while surface hardness contributes to its ability to resist wear from occlusal forces. Typically, a flexural strength within the range of 50 to 150 megapascals, combined with an occlusal surface thickness of 2 to 3 millimeters, is considered adequate for most applications. It's important to stay updated with the latest material specifications and research findings to make informed design choices. For specifics on materials like those from Medit or the latest in 3D printing materials, consulting recent studies or manufacturer guidelines is advisable. The slide discusses the use of the articulator open feature in a splint design application and its effectiveness compared to adjustments for a real open bite. The articulator open feature virtually opens the occlusion to design the splint, which has shown surprisingly accurate fit upon initial use. A comparison has been made between a splint designed using the articulator open feature and adjusted to a real open bite scenario, highlighting the differences in occlusal adjustment patterns. This examination sheds light on the practical applications and outcomes of using virtual tools in dental splint design, specifically in managing occlusal adjustments. Focuses on the appropriate thickness for the buccal and lingual walls of occlusal splints, recommending a range of 1.5 to 2 millimeters. This thickness is considered to provide an optimal balance between ensuring wearer comfort, maintaining splint durability, and fulfilling its functional requirements. Emphasizes that while 1.5 to 2 millimeters is typically advised, adjustments might be necessary to accommodate specific patient needs, the intended application of the splint, and the characteristics of the material used. Printing angle. This presentation focuses on evaluating the outcomes of printing at different angles 0, 15, 30, 45, 60, and 75 degrees. The objective was to identify which angle provides the best print quality and accuracy for a specified application. The findings indicate that printing at a 0-degree angle yields the most favorable results, suggesting that this orientation offers superior quality and detail accuracy compared to the other angles tested. Improving the transparency of 3D printed parts after post-processing, which often results in an opaque finish, involves several considerations. Techniques such as polishing, using clear coatings, or optimizing the printing and post-curing processes can enhance clarity. Material selection also plays a crucial role, as some resins are designed to yield clearer results post-curing. Adjusting printer settings for higher resolution and finer details can reduce surface roughness, contributing to a more transparent finish. We explore how varying the print layer thickness affects surface finish, particularly focusing on the superior gloss observed at 20 micrometer. As the layer thickness decreases from 100 micrometer to 50 micrometer, and finally to 20 micrometer, there is a notable improvement in surface smoothness and clarity. The finest layer setting of 20 micrometer results in a surface that captures and reflects light more effectively, enhancing the overall gloss and aesthetic appeal. This observation underscores the importance of layer thickness in achieving desired surface quality in 3D printing applications. To achieve a transparent and glossy surface on your 3D print, follow these steps. After printing, remove the item from the printer and detach it from the plate. Carefully remove any supports and smooth the surface. Apply a thin resin layer to the splint's exterior to enhance glossiness, and blow air to eliminate residual resin inside. Proceed with post-curing and finalize with an alcohol wash. The key to a high-quality finish is the final alcohol wash and maintaining a thin resin layer on the surface before post-curing.
Thank you for sharing all your tips with us, Dr. Kim. So let's move on to Q&A session. So today we have 4 questions in total. So I'll start with the first question. Question number 1. Which part do you think is the most critical part when it comes to reducing chair time in splints?
To reduce chair time in splint maturation, it's essential to ensure the splint fits securely without being too tight, allowing for easy placement and removal while maintaining effectiveness. This balance reduces the need for adjustment during delivery. Next, accurately capturing the occlusal bite by elevating the occlusion and using mandibular movement recordings for a corresponding antagonist model is crucial. This technique minimizes occlusal adjustment by aligning the splint with the patient's natural bite and movement, streamlining the fitting process and enhancing efficiency.
Okay, question number 2. Is it easy to use the Medit Splint app? I know that other companies also have Splint app, but what are the distinctive features of Medit Splint app?
The Medit Splint app stands out for its user-friendly approach and automated workflows, which simplify the design and manufacturing of the dental splint. Key distinctive features include its integration with Medit scanners for high-quality digital impressions, customization options for patient-specific needs, and notably, its availability free of charge. This combination of ease of use, cost effectiveness, and quality integration make the Medit Splint app an attractive option among the dental professionals, especially those new to using digital tools for splint production.
Okay, so question number 3. Do you think is airway essential when designing splints?
Yes, considering the airway is essential when designing a splint. Research has shown that patients with sleep apnea may experience an increase in apnea episodes and an intensification in bruxism frequency and severity when prescribed a splint that doesn't account for airway management. Therefore, it's crucial to assess for sleep apnea and differentiate between prescribing a simple splint and a mandibular advancement device. This method makes sure that the treatment doesn't accidentally make sleep breathing problems worse and meet the patient's need well.
Okay, question number 4. What's the most effective way of diagnosing TMD?
Diagnosing TMD effectively involves a comprehensive approach using a TMJ chart and a detailed questionnaire, including screening for sleep apnea. This method combines an assessment of symptoms and jaw function with the evaluation sleep-related factors, acknowledging the link between sleep disorders and TMD. It allows for accurate diagnosis and helps in creating a personalized treatment plan addressing both the mechanical aspect of TMD and related conditions like sleep apnea.
Okay, thank you for answering all the questions. Okay, so that's all about it for today. So you'll be able to watch this webinar on our YouTube channel and Medit Academy once it's completed. Thank you for being here, Doctor.
Thanks everyone for joining us today. Hope to see you at our next webinar. Bye.
Bye.